So I'll be talking about streaming and using a new platform called Heron. And before starting my own company just a month ago called Streamlio, that is focused on a lot of infrastructure, end-to-end real platform using streaming, I used to be at Twitter and managing the real-time compute team. So anyway, so I just want to give a glimpse of why real-time is the key. So in the today's information age, a lot of data is coming at a high velocity at you. So some of the data includes the Twitter feed, like a social media, also data from Game of War or games, or there are other data that like financial trading data and all this various data is coming at a high velocity at you. And more, as sensors and other things are being installed in the world, we are moving into more of a real-time connected world. And a lot of things like Internet of Things, like healthcare, as well as data coming from connected vehicles and digital assistants and augmented reality, these things are going to generate a lot of data and also at high velocity. So now, if you look at the value of data to its decision making, it kind of reduces. In the sense like the data has the highest value when the moment it is produced. But as it ages down, the value for the data goes down very quickly. So what I will be talking about is how we can harvest the analytics as well as the ability to process the data when it is the moment instant it is produced, like in the real time, or into the seconds range. I won't be talking about the reactive and the traditional historical data analytics. So what we used to use at Twitter was Storm. How many people have used Storm or have heard about Storm? Not bad. So, in fact, if you know, if you look at the history of Storm, Storm was open sourced by Twitter in 2011 after we acquired a company called Backtype. And we were running Storm at a high production in the sense like around 3,600 nodes we were running. And so my team was the one who was managing Storm and encountering all the issues and what are the problems that we face in the experience. So what we did is like over a period of time, after operating like 2-3 years, we accumulated a lot of problems that was happening in Storm. And some of them issues include scaling, because since we are operating at 3,600 nodes, there are all kind of issues in terms of overloaded Zookeeper and not able to debug, all kind of issues like that. And then second acute problem was debugging. In the sense like if you wanted to debug a Storm job or a Storm topology, it's extremely hard because you cannot find out where the logs are going to be. And even if you get the logs, since it's a threaded-based system, all the data coming out of different threads are congregated into a single log file, and finding the log in a sequential fashion for a particular spout or a bolt is going to be a problem. So and it never had a consistent performance. In other words, sometimes it used to perform well, sometimes it used to fall down in terms of performance when the data is increasing. And we don't want to have two systems in place. If we wanted to say like introduce a new system to avoid all these Storm problems, but we want to have one system to manage. So that's when we were deciding what to do with it, whether to continue with Storm and invest in Storm, or write a new system, or take some existing open source and try with it. And at the time, we were evaluating Spark Streaming, Samza, and a couple of more candidates, and none of the solutions for streaming solutions never scaled to our extent, because one of the simple tests that we do is, can we do for 100 nodes? So we tried to run jobs on 100 nodes, and all of the systems pretty much failed on those. And then at that point, we figured out it's probably better to go from ground-up thinking with scalability in mind so that we can operate that system at a higher scale. So some of the goals for Heron are consistent performance at scale and easy to debug and tune, because you should be able to assign resources in a single cluster. And it should be fast and general-purpose streaming engine. You can, because there's so much machinery that was running on, because Storm API has been invested so much in Twitter's infrastructure that we used to run around 400 real-time jobs. And all these jobs use Storm API. So you can't expect a new system to come up on board and introduce a new API, because we cannot move the existing jobs unless you rewrite those from scratch. So which means it has to be Storm API compatible. And also, like since the workloads or the jobs that run on the Storm API have different requirements. Some jobs requires, hey, I want very low latency. And some jobs say, I don't mind the latency, but I need high throughput because I'm just processing a lot of data. So how do you balance these various different workload requirements into a single system rather than having one system for different workload? And we also wanted to move towards a model where we don't want to run it on our own cluster and maintain our own cluster. Instead, it should be what we call as a library model, where you link your application or a job with this library, then it can be launched into any cluster. So that cluster is maintained by somebody else or some other team within Twitter, or probably if it's in AWS, the scheduler is maintained for you by the AWS folks themselves. So the Heron has been running in production for nearly 3 years. It was completely replaced Storm 3 years ago at Twitter, and totally 3x reduction in cores and memory. After we get Heron into production, we reduced the number of nodes around 3,600 to just 1,000 nodes at that point. And it has a significantly reduced operational overhead. As I mentioned, in Storm, when we were operating it, we used to have this notion of a pager. Every week, one of my team members have to carry the pagers around. So during that pager week, everybody used to dread because the support calls were so many, like including 2 a.m., 3 a.m., 4 a.m. calls will keep coming. And that incidence was so high when we counted it. And after Heron went into production, we got 10x or 20x reduction in incidents so much that we had enough time to have a peaceful night's sleep. At the same time, we also had time to develop more features into Heron itself. So some of the examples of the shapes of the jobs that are running inside for Twitter, it includes, you can see very simple jobs to all the way to complex jobs. And this is a dashboard that we use to monitor the jobs so that you know if you have any troubles, then you can look at the graph and see what's happening. So the Heron is used at Twitter at all over the place, and that includes several use cases, and some of them includes real-time ETL, the extract, transformation, load, and real-time business intelligence. And some of the jobs in real-time business intelligence move data around 800 gigabytes per second. And so that those jobs run around 800 to 900 containers, I mean Docker containers kind of, and that is equivalent to 100 plus machines on a single job. And so the third one is spam detections, where we identify fake news and fake accounts and abuse. All these things are detected using spam. And real-time trending. I mean, how many of you have used Twitter? Do you know how there is a notion of a trends in the Twitter app that computes based on the tweets that are flowing through the system? It tries to bubble up the trends, and so that you know whether any real-time event that has hit or not. So, for example, if Trump made a statement that is making waves in the whole news circuit, you will see that trending because a lot of people in Twitter are discussing about it. So those are real-time trends are computed in Heron itself. And we also compute a lot of the ad prediction models and ad serving models based on machine learning. And we also process log data coming out of hundreds and thousands of machines that we used to have at Twitter. So Heron is open sourced at May 2016. If you're the Apache 2.0 license, and a lot of contributions from Microsoft, Google, Mesosphere, then Wanda Group, WeChat, the Chinese equivalent of Twitter, and Fitbit, and a lot of people have started trying Heron out, and it is going to be more and more communities growing around it. So now I wanted to go a little bit into the Heron itself so that you can get an idea of what it means. So let's introduce the Heron core concepts. So the first one is what do you call a Heron job is called a topology. And the topology consists of two different type of vertices. And one of them is called the spouts, which allows you to tap data into the source and inject data into the topology itself. And the second set of vertices is called bowls. And bowls essentially take data from a previous stage and manipulate the data, massage the data, or compute the data, and emit outgoing data for the next set of stages. To give a concrete examples, you can see two spouts, which are essentially tapping data into some sources, and which in turn pass the data to the bolt 1 to bolt 3, and which in turn process the data, pass on to bolt 4 and bolt 5. And the difference between Heron topology and a MapReduce job is you can have several stages in a Heron topology. As I said, like we have around 10 stages, 20 stages, as I showed you earlier. On the other hand, with MapReduce, you can have 2 stages. You have to have multiple 2-stage jobs, one feeding off of each other, whereas here you don't have to worry about the number of stages. And also, like, there's no notion of checkpointing in the sense like at every stage, the data is not stored into the disk. Instead, the data is completely streamed from one stage to another stage in memory and network so that the processing is continuous. So then if you look at how this topology is run in a physical hardware, so we have this notion of what we call the topology master. I mean, essentially, Heron uses this modern architecture called Docker containers or C group containers. So the first, whenever we launch a Heron topology, the first container that comes up is what we call as a topology master container. And that topology master looks at your DAG and finds out how many resources that you need, how much resources that you need to launch the job on the cluster. So for example, once the topology master says that, okay, I need around 10 containers for this job to run, so it will request the 10 containers from the scheduler wherever the scheduler that you're running the topology on, and then it says this container should be of the size like X CPU on Y amount of memory and Z amount of disks. And once you have that, then the scheduler will start those containers across the cluster, like 10 containers in our case, and those containers will look like this, where like the bottom containers. So those are the containers which are actually processing your data. So the first the process that gets started in the container is called the stream manager, and the stream manager is the one that is representative of that container. So first order of business for the stream manager is to discover where my topology master is, and in order to do that, the stream manager looks up the Zookeeper cluster, which is more of a distributed synchronization component. And every topology master writes, when they come up, writes where that particular host and port is, so that the other stream managers that are coming across these containers can discover where the topology master is, and then everybody reports to the topology master. So once all the containers that has been started by the scheduler is reported okay by the topology master, then the topology master constitutes something called a physical plan. And that physical plan is essentially gives information about where each of these containers is running, what machine and what port and all. And that physical plan is stored into a Zookeeper cluster for any failure of the topology master itself. And then that physical plan is broadcasted to all the containers. And the moment all the containers receives that physical plan, then each of these containers can connect to each other so that the data can be started exchanging. Then remember the spouts and other things that you saw in the DAG before, and those spouts and bowls, which are actually the user land programs that you return, your processing logic of the data and everything, will be running on these I1, I2, I3, and I4. These are nothing but what we call as the instances. And these are the instances that is actually running your user land code. And these instances are not thread-based in the sense like every task, every spout, and every bolt is running on a process of its own. And unlike Storm, where all these instances used to be running as threads within a single process, in Heron case, it used to run on only one process. The reason being the fact that when you have process, you have an isolation at the individual spout level and individual bolt level. And similarly, you have since the containers does not interfere with any other containers, you have isolation at the container level. Now, since each topology master manages only its topology, there's no interference from one topology to another topology. So that way, we can, if a job is penalizing itself, it will penalize itself only. It won't affect anybody else. So from a performance point of view, because the title of the talk is how to improve the latency of your streaming job so that you can do end-to-end computation very quickly within milliseconds. So the main bottleneck for the performance is the stream manager. The reason being the stream manager is all the data that is coming from the instances I1 and I2, I3, if they are destined for some other container, they have to go through that stream manager on that container, which in turn routes the data to other containers. So similarly, when the data is received by the stream manager from one container, it distributes the data to the instances and vice versa. So because of this, the stream manager is essentially the bottleneck where data goes in and comes in. So let's look at what are the stream manager design goals. So we designed the stream manager so that the core logic of moving data around is contained in only one place. And it's super efficient. Already it's very efficient, but we wanted to do it more. And it's also very pluggable in the sense like you can have your own transport. In the sense like if each container of the stream manager wants to connect with either a TCP sockets or unique sockets, or it can even use shared memory for all those kind of things. And similarly, like we wanted to introduce some kind of inter-language data format, something like the protobuf. How many of you have heard about Cap'n Proto? It's highly efficient and very fast indeed. And there is a new thing called flat buffers also, similar to protobuf, but flat buffers is supposed to not serialize, deserialize. Once the data is put down in the format, you can just ship the data as it is, and you can load it on that other memory, and you can just access it. There's no notion of serialization, deserialization as well. So then we wanted to use our own protocol, like either you can use HTTP or gRPC, or you can do custom, which we use for custom right now. So then multi-languages. So the instances your programs can be written in Python, or it could be written in C++, or it could be written in Java. But all the instances, irrespective of the language, whatever you do, it has to interoperate with each other. So the current implementation is, the Heron implements at most once and at least once, and is written in C++ for efficiency. Because the reason why we chose C++ is because it gives very high speed and low latency. And we use custom transport using TCP sockets. And it also uses protobuf data format. And then finally, you have a custom protocol, which is what we use. And that is highly efficient as well. Now, what are the shortcomings? Even though we implemented our first version and we proved that that's 10x or 15x faster than Storm, we took a step back and wanted to see how the performance is being affected. So we looked at the various other aspects, and I've grouped them into 3 different categories. One is transport shortcomings. TCP has some kind of overhead when you go across the nodes, and there were multiple memory copies. And the protobufs also has its own set of shortcomings as well. One is serialization, deserialization of data going from instance to stream manager, and going from stream manager to stream manager is expensive. And sometimes when we look at the field for routing the data to the appropriate stream manager, you have to do a full deserialization before we can access any field in the first place. And we also were doing a lot of new and delete calls. So when we get a message, new, put the message, then after that deliver the message, then delete the message. So there was a constant new and delete calls. Then finally, it follows an immutable pattern, which is once a protobuf is formed, you cannot change it. Then easy to reason, but it's highly inefficient. Now, we did a complete performance analysis of the stream manager to figure out where the time is actually going. So in order to do that, first we tried Valgrind. How many of you know Valgrind? Nice. So it was too slow and too much overhead, and we are not able to change what we are trying to observe. So then finally, we used the Google performance tools. There's a small kit that's available, and it was very fast and doesn't do code instrumentation, and we can do CPU profiling, memory profiling, all in one tool. So when we did the performance analysis, we found out 17% of the time is going in new and delete calls. Whenever you get a message, you do a new on that message. Once you deliver the message, you delete. 17% of the performance went there. And 50% is because of the immutable pattern, where the protobuf is never changed on the fly. Then 15% of another performance bottleneck was with eager deserialization, which means you deserialize before you even have the need to look at the data. So then 12% is for protobuf size related, where if you wanted to compute the size of the protobuf, like computing the number of bytes that message takes, that takes 12% of the time too. So once we identified just how to optimize. So how do you take the new and delete overhead? So we create the problem is we create a new protobuf object every time we read and write messages. And the protobuf sacrifices speed for safety, but since we wanted speed, And the safety is something that we can consider at the user land or the code that we wrote. So we decide to do it for speed. And the solution was we create a protocol of pools at startup. In the sense like we do new only when the pool is exhausted. Otherwise, we reuse memory out of the pool itself so that you don't have the new and delete cost anymore. So the pool is bounded in size so that you don't blow up the memory of the whole container itself. So that is bounded by a certain amount, and that will reach a steady state once the topology reaches a steady state as well. So the optimization 2 is immutable pattern. In general, one tuple can fan out to multiple downstream instances because when you do, if you look at Storm, when the data is routed, you can route the data to multiple instances at any given time. So for each downstream instances, we made a copy. So whenever the same copy is being sent out, we are sending copies and copies of data. So instead of doing that, we just do an early serialization to create an immutable array and just copy the raw bytes. So which means only one single copy is kept instead of taking copy for every instances. Just one readable copy and send the raw bytes. Then the next one is eager deserialization. So protobufs deserialize the entire message even if you wanted to look at only one field, because we have to look at one field to route where the data has to go. So the solution is we change the protobuf message format so the payload is raw bytes, which you don't have to look at. The header is the only thing that we have to look at, which does not have to be serialized and deserialized. Then optimization 4, again, calculation of protobuf byte size. So instead of the byte size computation is so expensive, like we saw 12% of the time going there, right? So instead of computing every time from scratch, we use something called a cached byte size, where the size is kept around. And so once we did this, so we said, okay, let's try to benchmark it. How faster did it get? So to do that, we ran the whole experiments in Intel Xenon are running at 2.4 gigahertz with 12 cores and each two hyperthreads, and that is 24 cores each, with 72 GB RAM and 500 gigabits disk. And this is a simple word count topology where we are generating 175,000 words randomly and blasting that data through the topologies where the words are being counted. And we varied the spouts and the bowls from 25 to all the way to 200. And as you can see, in the utmost ones where the data is processed with the best effort, if there is any loss of data because of failure, that's done, and we don't do anything about it. But with this case, the throughput improved by 5 to 6x. So as you can see, like in 17 machines, you can do 170 million tuples per second at this point with the new performance. So then we looked at how much throughput per core that we are getting compared to the previous versions. So we are getting around 5 to 6x improvement in throughput itself. Now look at at least once throughput. Again, the same story. We got around 4 to 5x increase in throughput with the optimizations, whatever we talked about. And again, the throughput per core also improved drastically. Then finally, with latency. I mean, latency is measured as the time that the data entered the topology versus completed its processing, and this acknowledgements coming back all the way to the source itself. And that also got improved by 2 to 4x. You can see the lower latency that we got is around 23 to 24 milliseconds. Now, in the current experiments, we have reduced down to 13 milliseconds. And if you use, instead of what you call Ethernet, and if you use InfiniBand, you can even do like 6 milliseconds. So, which means we have got the latency for a streaming solution as low as 6 milliseconds, which the financials and the Wall Street folks love it because of the fact they wanted to do high frequency trading, and every millisecond is translated into millions of dollars. So if you are curious to learn more, we have written a bunch of papers ranging from Storm at Twitter, what are the problems Storm faced, and why we designed Heron's streaming process and scale. Then if you wanted to know about Storm performance versus Heron performance, Heron is already 5 or 6x even faster than Storm itself. And that numbers are available in Twitter Heron towards external field streaming engines. This is the paper that got published in ICDE 2017, just a couple of months ago. Then we have 2 more papers which we published called Distributed Log This is for storing streaming data and all. Then this is the last paper that is going to come up in the next VLDB, which is in October. That is taking streaming to the next level where you don't have to deal with tuning and all the manual aspects. Once you just launch topology, you're done. It will automatically adjust itself, either throughput or latency sensitive or anything, whatever you want to do, it will adjust itself. You don't have to do anything. So it is taking streaming to the next level. Then that's all I had. Any questions? Okay, thank you.